Welcome back to DeepVisus, where vision meets depth. I'm your host, and today, we're embarking on the final leg of our journey through Part 4 of Understanding Intelligence by Rolf Pfeifer and Scheier. We've explored the foundational principles of embodied cognitive science, from complete agents to parallel processes and active perception. Now, we're ready to uncover the driving forces behind an agent's learning and how this shapes something as intricate as memory itself. Our focus today is on chapters 14 and 15. Last time, we discovered how an agent's active engagement with its environment through sensory-motor coordination can simplify complex learning challenges. But even with the ability to structure its own input, how does an agent know what's important to learn? How does it decide which interactions are beneficial and which are not? And how does this fundamental drive influence something as seemingly abstract as human memory? These are the questions we'll tackle in this episode. Chapter 14 introduces a crucial concept: the value principle. This principle states that for an agent to be truly autonomous and situated in the real world, it needs a built-in value system. This system acts as an internal compass, guiding the agent to judge what is good or bad for it, and crucially modulating its learning process. Think about it. If an agent is constantly interacting with a complex environment, it needs a way to filter the endless stream of sensory data and prioritize what to attend to, what to learn from, and what behaviors to repeat. The value system provides this crucial feedback. The authors distinguish between two types of value systems. Explicit value systems. These generate clear, internal value signals, which could be neural or even hormonal in biological systems, or specific digital signals in artificial agents. These signals directly influence the learning rules, for example, by strengthening connections in a neural network when a beneficial action occurs. Imagine a robot successfully grasping an object. This success triggers an internal reward signal that reinforces the grasping behavior. This is the core idea behind reinforcement learning, a powerful learning paradigm where an agent learns to maximize rewards or minimize punishments through trial and error, without an external teacher explicitly telling it what to do. The challenge here is the credit assignment problem, figuring out which specific action or sequence of actions led to the reward. Implicit value systems. These are more subtle. They involve built-in mechanisms like reflexes or morphological biases that naturally increase the probability of an agent getting into situations where it can learn something useful. For instance, a simple reflex that makes a robot turn towards a light source might implicitly guide it towards a charging station, creating opportunities for the robot to learn about energy replenishment. These implicit values provide the initial motivation for the agent to explore and interact in ways that are likely to be beneficial. The value principle emphasizes that learning must be self-supervised and incremental. The agent learns continuously, guided by its own internal value system, rather than relying on a human designer to provide correct answers. This continuous, value-driven learning is essential for true adaptivity and for the emergence of complex, goal-directed behaviors over time. It suggests that motivation itself is not a separate, high-level module, but an emergent property of these value-guided processes. Now, how does this active, value-driven learning relate to something as complex as memory? Chapter 15 tackles this head-on with a compelling case study on human memory. Traditionally, memory has often been conceptualized as a passive storage and retrieval system, much like a computer's hard drive. We have sensory buffers, short-term memory, and long-term memory, where information is encoded, stored, and then retrieved like files. However, the embodied cognitive science perspective offers a radical reinterpretation. It argues that memory is not merely about storing static representations. Instead, it is deeply and fundamentally intertwined with sensory-motor coordination and the agent's active interaction with its environment. Consider how infants learn about objects. They don't just passively observe. They actively touch, grasp, turn, and even mouth objects. This active physical engagement helps them to structure their sensory input, generating consistent patterns that are crucial for forming categories. From this perspective, memory isn't about pulling up a static image or a pre-recorded fact. It's about the capacity to reenact or reconstruct past sensory-motor coordinations. When we remember an object, we're not just retrieving a picture. we're reactivating the patterns of interaction we've had with that object. This view has profound implications. It suggests that memories are inherently grounded in an agent's physical experience, directly addressing the symbol grounding problem we discussed earlier. Memory becomes dynamic, context dependent, and constantly reshaped by ongoing interactions and current values. It's not a fixed archive, but a living, evolving capacity for interaction. The frame of reference problem is key here. Our everyday descriptions of memory as stored information might not reflect the underlying, active, and distributed mechanisms. So, to answer our guiding question, agents decide what's important to learn through an internal value system that guides self-supervised, incremental learning. This value system, whether explicit or implicit, provides the feedback necessary for the agent to reinforce beneficial interactions. This active, value-driven engagement with the environment through sensory-motor coordination is what fundamentally shapes memory. Memory, in this embodied view, is not a passive storage of facts, but the dynamic capacity to re-engage with the world based on past experiences, constantly adapting and refining its understanding through continuous interaction. And with that, we conclude our exploration of the principles of intelligent systems in understanding intelligence. Join us next time on DeepVisus as we bridge the gap between theory and practice, diving into the exciting world of agent design and evaluation, and uncovering the secrets of how these principles come alive in the robots and simulations shaping our understanding of the brain, mind, and intelligence. Prepare to see how the abstract becomes tangible